All right, let's get into some applications of these rational functions that we've been working on graphing. This is a pretty classic one. There's all sorts of variations on it. This is absolutely the type of thing that you'll be working on in calculus, and you'll be able to hopefully do all of this without technology at that point, but we will use technology to help us answer some parts of this. I think the biggest focus for us right now is actually the setting up the formula part. So our example here is that Marie is trying to make a rectangular box. She decides that she's going to have a square base on her box, and there's a fixed surface area. So basically I would describe that as she's fixing the amount of material that she needs to make the box. Her goal is to have the largest possible volume with those restrictions. So I always recommend drawing a picture. Really important here is the square base part. That's going to allow us to not accidentally get some extra variables in there that'll make our life way harder. Okay, that does not look exactly square, but hopefully you get the idea. Hold on, I can't leave it quite that crooked. Okay, and then there's the thing coming down, and we do have this. Part A is asking not for the volume formula, that is our goal, we'll get there in part B, but it's just asking if you can find a formula for the height of the box, assuming that the base has side lengths x centimeters. So we're imagining it's a square, which means both side lengths are going to be x, and then this is the height h that we're talking about. Okay, so if we look back up and we say, what is actually restricting this? Why can't h just be anything? Why in the world would h depend on x? The only thing I can see that might make that true is the surface area. So let's start thinking about surface area. I'm just going to use A for that. We'll define surface area. To find the surface area of this box, we would have the base, which is dimensions x by x, so x squared is the area of the base. This doesn't actually specify whether or not the top of the box is open, and usually they do, so I'll try and make sure I'm really clear about that on test questions and the like. But let's just assume there is a top to the box in this one. So there would be another x squared on the top. And then we have to worry about the sides of the box, right? And there's 4 of those. And because the base is square, all 4 of them will be identical. So we're going to have 4 sides, and the dimensions of each side are x and h. So its area is h times x, or x times h. Like I've said probably before, I like to alphabetize just to have some sort of order. And I can combine those x squared. So we have 2x squareds and 4hx's. And this is supposed to equal our surface area, which is 96 centimeters squared. Fantastic. We have a formula, but it's not quite what we were asked for. We were asked for height as a function of h. So as soon as you get a relationship between h and x to make h a function of x, you can just solve for h. So that's what we need to do here. So I will subtract the 2x squared from both sides and say 4hx would then have to equal 96 minus 2x squared. And then we'll need to divide by the 4 and the x. So we can say h is 96 minus 2x squared over 4x. And you can split that fraction up and reduce a little if you want. I think I'll just leave it for now. If it seems like I want to simplify later, I can do that. So that's height as a function of x. My next task is to write the volume formula. So I have to think about this. This comes from geometry. If you don't already know this one, it's worth memorizing. Length times width times height is the volume of a box. And sometimes I'll make this extra step just to write that out in words. I do find that writing it always out with variables, L times W times H, sometimes causes trouble because you may have already used that variable for something else. I don't think that would be true here, but just as a warning, if that's getting you a little confused, just write it out in words and then start to fill it in. One nice thing here is that the length and the width of the box, I'm just going to consider the base. This is length and width, and then h is height, which makes sense to me. The length and the width are the same, so this is really x times x, and then this is very nicely structured for us. The work we just did gave us the height as a function of x, so 96 minus 2x squared over 4x. And I think I will try and simplify at least a little bit now because something's jumping out as being really easy. I can cancel an x out, and I might even go a little further and factor a 2 out of the top so that I can cancel that. So I have x, and I think I'll write that x over 1 just so that when I mush these two together, it doesn't look confusing. On the top, I'm just going to factor that 2 out, and that should leave me with 48 minus x squared over 4 because I've already canceled an x out. And then let's just reduce a tiny bit more. We can cancel a 2. So when I put this all together, I have x times 48 minus x squared over 2. So this is my volume formula. And the next task is going to be to graph this thing. I would say for these applications, sometimes the graphing gets a little messy. What we're hoping for is that all this work we've done gives you some decent intuition about what this thing will look like. And then we can use technology to shore up some of the details. So this one actually didn't end up being rational when we were done. It was rational for a little while. And I guess technically it still is, right? Because what would be happening here is that there's a removable discontinuity at 0 since I canceled an x out. But in terms of graphing, I'm expecting to get a polynomial with a hole in it. So we're mostly going to want to only see positive values. This is volume as a function of side length, so those should both be positive. But just in terms of keeping track of where some things happen, we're supposed to have an x-intercept at 0. Oh, this is interesting. So zeros, I'd want to say 0, 0, but actually that's a hole, right? So this is kind of a tricky exception here where even though we canceled an x out, we know it left a hole. There's still that factor of x there. It does make it easy to see where it is. So there's a hole at 0, 0. And then the zeros will come from the 48 minus x squared, which means they're at plus or minus the square root of 48. So we'll say this is root 48, and then this is kind of ugly, but out here somewhere would be negative root 48. Again, I don't really want to keep that, but it'll help me get started on my graph. And then there's a hole. Global behavior, if we multiply that out, we'd get negative x cubed. So we're going to be starting from positive infinity, and we'd come down and we'd cross at negative 48, and then we'd have to cross again at 0, and then we'd go up, and we'd have to turn around and cross at 48, and then it would just keep going to negative infinity. So it's really just that little chunk right there, that cubic part that we're interested in. We can check ourselves with technology, and we can also use technology to answer the rest of the question, which was what value will give the maximum volume. So here it is in a standard window. I'm really thinking I mostly just want to see 0 to 5, and even with a little fiddling around there, I am going to need to adjust my y's a little bit. So let's just play around a little. That's at 8. It looks like I need to go quite a bit further. Let's try 30. That's still looking like I didn't catch the top, so maybe 50. Still not looking like I quite caught it, but closer. 75. There we go. Okay, so there it is. I can actually see the maximum, and we can click to get a more precise answer. It's 464. Quite a nice answer we actually got there. Okay, so let's jump back in and answer the question. We found that this was at 464. Oh, I can't write what I'm saying. 464. So what value of x gives the maximum volume? My answer to that would be x equals 4 gives the maximum volume. All right, and then there's one last little bit to this that I think is kind of interesting. We're supposed to add a graph of h of x and see if we can use it to find the height that gave us that maximum volume. So here is the graph of h of x, and you can even call it h of x if it helps to keep track, added to the graph of our original volume function. And what we know is that volume was maximized when x equals 4. So if we want to figure out the volume of H that goes with that, we're actually looking for the one that shares the exact same X value. And it looks like, if I can click on it, ooh, let's see if I can get it. I'll show you how to force this too. Oh, I think I saw it. I think it was a 4, 4. Okay, so if you're having trouble getting it to do that, remember you can just say X equals 4 is what you're interested in. It'll put a vertical line and then you can click on it. So it looks like the maximum possible volume is actually coming from a cube. So let me jump back and make sure that that makes sense as a conclusion here. So looking back at the original picture of our box, what we're saying is that X equals 4, which means both dimensions of the base have to be 4. And then we just found out that the height also has to be 4. So to maximize the volume of our box, we actually just set all dimensions equal and we get a perfect cube, and that maximum possible volume is this 64 right here. I do want to show that you could answer this question algebraically. I just think there's something nice about trying to get your brain to look at that graphically. We have a formula for H. So if we know that X has to equal 4, we could absolutely snag that for this last part and say, well, let's just plug in that 4. And that's the formula we get. And if you calculate that, you should, in fact, get that exact same 4. What are we doing? Centimeters. So having dimensions 4 by 4 by 4 will maximize this. Note that this will change if we leave off the top of the box. It will change if we mess around with this at all. But if you don't have anything else weird going on, the maximum possible volume of a rectangular box will come from making it a cube.